Hello friends, welcome back to my channel. So it is part 2 of chapter number 5, and in this chapter we will take epoxidation reactions, and then we will see some different type of epoxidation, that is sharpness epoxidation. So we all know about sharpness epoxidation reaction, but we will see some different features of that also, right? So first we will try to understand our basic epoxidation reaction. So you know that for epoxidation we need a double bond and a per acid, right? And the reaction proceeds by the attack of this oxygen on this double bond, and this attack is due to its electrophilic nature, right? Double bonds will act as a nucleophile and it will attack on this electron deficient oxygen. Then this bond will shift here and this will shift on this oxygen. Because of this shifting, this oxygen will become electron deficient. That is why this double bond is attacking on it, right? So basic thing to understand here, this oxygen, this per acid is acting as a electrophile and this alkene is acting as a nucleophile. So whenever we have a electron withdrawing group on per acid and electron releasing group, or you can say electron donating group on alkene, both condition will increase the rate of epoxidation, right? Because electron donation increase the nucleophilic nature of this double bond, and electron withdrawing group attached on per acid will increase its electrophilic nature, right? So basic thing we have understand here. Then we can solve questions. That suppose I have here two double bonds, so whenever I have one equivalent of MCPBA, only this one participate first, right? Now you can easily identify that this double bond is attached with two alkyl groups, means it will be more electron rich as compared to this one, right? So it will first react with this MCPBA and will be epoxidized, and this one will remain unaffected, right? Or other conditions can be possible, that if you have your double bond in conjugation of some electron withdrawing group, right? So your alkene is next to a group which is electron withdrawing in nature, means decreasing electron density over it, right? Means this pi electron present in this double bond is participating in conjugation. That is why it is not easily available for donation, so its epoxidation ability will decrease, right? So whenever you have this type of groups, most of the time MCPBA is used with high temperature conditions, right? Strong per acids are used, we can use strong per acid for them. We can use MCPBA at high temperature. One possibility is this. Other possibility is when you have this alpha beta unsaturated ketone aldehyde, then in such cases we use different type of epoxidizing agents like H2O2 in presence of NaOH, because the epoxidizing nature of this H2O2 is due to its electron donating ability, right? Means this H2O2 is acting as a nucleophile in this epoxidation reaction. That is why it can give its electron to this pi bond which is electron deficient due to its conjugation, right? So whenever we are doing epoxidation of alpha beta unsaturated carbonyls, then you need H2O2 in presence of NaOH. And when you have double bond rich in electron, then you can use per acids because they are electron deficient in nature. So both of them are epoxidizing agents, but their nature is different. So it is very important to remember this. The next important thing which we all know, but sometimes we may confuse over it, that this reaction is stereoselective in nature. Stereoselective means if you have cis alkene, then cis epoxide will form, right? This thing is very easy to understand, that you have a alkene like this, and upon epoxidation it will give you epoxide like this, right? Or if you have E alkene, then it will give you E epoxide, right? So this is very simple thing. But when you are drawing such type of structure in the complex structure form, you may have sometime confusion that this is your E alkene. So upon epoxidation, what type of structure you will get? You have to draw one carbon-carbon bond in dashed form and one in wedge form. Means in this case you will get this type of structure. One bond is in different plane and another one is in different, right? So this type of simple thing can be applied like this. Now you can do it easily. Then we will move on to something very different, and we are very familiar with this also because we have seen number of example based on this, that whenever we are using MCPBA with such type of alkenes, then major product is where your epoxide will attach from the different plane of the bulkier group, right? Because of, to avoid hindrance, this oxygen will attach from the different side, right? And in case of OH, this thing will not apply because hydrogen bonding can take place. So OH and epoxidation will be on same side, right? So it is very simple. I will not go in detail of all this. Then you may have such type of structure also, allylic alcohol, right? So we have discussed about such type of alkenes, cis and trans arrangement of in allylic type of bonds in Clayden book summary, and where I have discussed Houk's model. So this is slightly different than Houk's model, but you can revise that thing from there also. Here I will say only that when you have such type of arrangement, that you can draw it like this, that your double bond is like this, then on this carbon you have this methyl, this bulkier group, and H. So in this case the most stable structure is when H is in eclipse form of this double bond, and this bulkier group will go away from this double bond side like this, and Me will go like this, right? So in this case epoxidation will be done from this side, above the plane side, from top side. You should say that from the top side, to avoid this, because at this side we have cavity like structure, so we should not go like this, we will go from top side, right? So when this epoxide is suppose attaching top side and we are denoting it by above the plane side, then this methyl is on the different on the opposite side, right? So we will draw it below the plane, right? So as I have said you earlier, that if you want to go in detail of other type of example, you can watch this Houk's model from the Clayden book summary. I will provide the link of that particular chapter in the description box, so you can watch it there. Then we will move to other epoxidizing agent. So MCPBA is very familiar for all of us, but sometimes in reactions they may give you different type of epoxidizing agents, and sometimes you will not recognize them, or you may have some confusion that what we should do with them, right? So I will tell you all the other type of epoxidizing agent, then you can easily do that reactions also. First possibility is you can have tertiary butyl hydroperoxide, you can write it like this, in presence of, you can have vanadium catalyst, vanadium fifth catalyst, you can have molybdenum sixth, or you can have titanium fourth. We all are familiar with titanium catalyst, but you can also have vanadium and molybdenum complexes, right? So first I will tell you that what are the different type of chemoselectivity of these complexes. And vanadium complexes are very efficient in reacting with allylic alcohol, right? And this molybdenum is good for isolated double bond, right? So we have here one example where we are using this tertiary butyl hydroperoxide, along with we have vanadium complex as a catalyst, right? So in this example we have two type of double bonds, this one is allylic and this one is your isolated double bond. So here we have discussed that they are good for vanadium catalyst, but vanadium complexes are good for allylic alcohol, so epoxidation will be done on this double bond, right? It will remain unaffected. So you can write down these different type of epoxidizing agents in this bullet forms, then you can easily remember them, right? Then we will move to one more example. Again we have the same type of catalyst. So this type of example is taken, that we have here OH at allylic position. So we have two possibilities. that this epoxidation and side of attachment of OH is same, and we can have opposite side of their attachment, right? We have discussed already that MCPB also show same type of feature, that the attachment side of oxygen and OH is same. In the major product is in which they are on the same side. Same type of selectivity is also shown by this vanadium complex. But what is the use of this example here? That this stereoselectivity is much better in case of vanadium complex, that you will get 90:10 ratio of this two products. If you are using MCPB only, then you will have 52:48% ratio. So they are better stereoselective in this reaction. Next example is that we have seen that allylic alcohol are good for epoxidation using vanadium complexes, or we are using titanium complexes. In addition to that, these complexes, either you have titanium, vanadium or molybdenum, they are also good for homoallylic alcohols. Homoallylic, how you can identify this homoallylic double bond? So in case of allylic you have OH here. When you have allylic alcohol, OH is present on this carbon, right, next to this double bond. But in case of homoallylic, you have one more CH2 in between this double bond and carbon containing OH, right? They can also show same type of feature. So again I am using the same catalyst, that is tertiary butyl hydroperoxide, and again the vanadium complex. So it will give me major product in which the side of attachment of this oxygen and OH are same, right? And if we are using a different type of complex, that is molybdenum complex, we have seen in previous slide that molybdenum complexes can also show epoxidation, right? And I have said that they are good for isolated double bond, but they can also attack on allylic alcohol. But in case of titanium complexes, they will not attack on isolated, they will only attack on allylic alcohol. So we will take detail of this titanium complex a little bit later, but first we will understand this one, that this is again your homoallylic, because oxygen is not attached on this carbon. We have one more CH2 in between this carbon containing OH and this double bond, right? So it can also show same type of epoxidation. Let's take some more type of epoxidizing agent. We have seen this tertiary butyl hydroperoxide in presence of metal complexes. We can also have hydrogen peroxide, right? And we can use different type of metal complexes here, like this rhenium complex, right? In this reaction, cyanopyridine is also, other pyridines can also be used to increase the rate of reaction, right? So again epoxidation will be done similar to the previous cases. So in this case you will get epoxide like this, right? We have one more oxidizing agent, that is epoxidizing agent, that is DMDO. DMDO is dimethyl dioxirane. So how you can synthesize this dioxirane? Because in sometimes in reaction they will not directly give you DMDO, but they can give you a ketone. For example, in this particular case, because we are synthesizing dimethyl dioxirane, so we will use acetone, right? They can give you acetone plus oxone. Oxone, we have discussed about oxone in previous chapter, in first part of this chapter, that is oxone. Oxone is a mixture of different type of potassium salts, right? But the main ingredient is KHSO5. So they may give you oxone plus acetone, or they may give you acetone plus KHSO5. So how it will be synthesized? That first step is this HSO5 will attack on this carbon, so it will attack on this negative charge, will attack on, and this bond will shift here. So you will get this type of structure, right? This is your dioxirane. When your carbon is attached with two oxygen like this is your dioxirane, because we have here two methyl groups, that is why it is dimethyl dioxirane. So it will act as a epoxidizing agent. You may also have different type of dioxirane which can act as epoxidizing agent, right? You may have different acetone here, KHSO5 will be there, but you may have different type of ketones, then different dioxirane will be formed, but the main purpose of their use is they will do epoxidation, right? For example, in this case they have given us simply DMDO, dimethyl dioxirane, and uh, dichloromethane is used as a solvent. So epoxidation will be done on this carbon. Simply you have to do epoxidation from the less hindered side, because these two groups are attached on above the plane side, so epoxidation will be done on below the plane side, right? This will be your product. So we have seen that other dioxirane can also be used. Last epoxidizing agent is oxa oxaziridine. They are also good epoxidizing agent. I am telling you these different type of epoxidizing agent here in this slide, in this video, because there in the past years there are lots of questions on MCPBA, and there are very good chances that in future they may give you different type of epoxidizing agent, right? So you should be familiar with them also, right? There is no way, not so much difficulty in their reactions, but you should be familiar that these are epoxidizing agent, so you can easily recognize them and do the epoxidation reaction, which is very easy and you can easily obtain marks for them, right? So how we can synthesize this oxaziridine? They will not directly give you this oxaziridine in exam in question. They will give you iminium salts. You can recognize imine, right? And from this imine, this iminium salt will form. And this, suppose I have this iminium salt here, and along with this iminium salt they will use this again KHSO5. So this KHSO5 will do epoxidation of this iminium salt like this. Then it will attack on double bond to give you epoxide, right? So simply you have to recognize that we have here a iminium salt and KHSO5, so we can do epoxidation here. We have here E alkene, so if it will give me E epoxide, right? So these things are very very easy, but you should revise them, right? Then we will move to asymmetric epoxidation, sharpless epoxidation reaction. So we have seen lots of example and lots of theory based on sharpless epoxidation. So I am not going to tell you only the basic things about this sharpless epoxidation. We will also see some different type of example, right, which can give you a confusion. Many times you may have confusion with them. So first I am going to tell you that what conditions are required in bullets form only. So first important thing is you need allylic alcohol. Only allylic alcohol can show sharpless epoxidation. Then you need a epoxidizing agent. Tertiary butyl hydroperoxide is used. Titanium complexes are used, and along with them we need a tartrate ligand. Most of the time diethyl tartrate is used. Diisopropyl tartrate can also be used. And the important thing is the attachment side of oxygen, right? So this is decided on the basis of your plus and minus det or DIPT. So what should be the basic condition how you can do this reaction? You have to draw your allylic alcohol in such a form that this double bond is in vertical form, right? And this hydroxymethyl group, this is your hydroxymethyl group, it should be on the lower right hand side, right? And here you have one more alkyl group attached. This should be the condition. Always remember that you have to place your allylic alcohol in such a form that your double bond is in vertical form and this hydroxymethyl group is on the right hand side, right? If you have such type of configuration, then your plus det or DIPT will attach oxygen below the plane, right? You can use different mnemonics to remember these things, or you can simply remember this, right? Sometimes mnemonics can give you confusion at the time of exam. So this is very simple, that plus with plus oxygen will go below the plane and opposite will be happen with minus det, that oxygen will go above the plane. But this condition should be matched, that your double bond is in vertical position and your hydroxymethyl group is on the right hand side. This condition should be matched. For example, in this particular case, other reagent should be there, that is your tertiary butyl hydroperoxide, titanium complex and this. So I am just writing only plus and minus det, right? All conditions should be there. I am not writing them again and again. So you can have two conditions here. So with plus det, what you will get? Below the plane attachment of oxygen, and with minus det, oxygen will attach above the plane, right? Suppose again if I have same type of conditions and we are using here minus det, right? So first thing is we have two double bonds, but only this one will participate because it is allylic alcohol. This isolated double bond will not participate in reaction, right? Then you have to draw this double bond in vertical form. We have nothing to do with this part. This alkyl part is not of our use. We will only see that if we draw it like this. Suppose I am rotating this in this form. I am rotating this molecule like this to place it in vertical position. I am rotating it by 90 degree, right? So when you will rotate it, this bond which is on our side will go on right hand side, right? So you will get this type of configuration, means your hydroxymethyl, this carbon bond is on the right hand side, and which is required for our condition that minus det will show above the plane attachment, right? Then we will see some more example. I'm telling you that I'm taking only examples which are difficult, right? I'm not taking the basic type of examples. Here we have again allylic alcohol, right? So conditions are similar to previous one, but in first case suppose I have plus DIPT. So you have to first draw this double bond in vertical form when you rotate it by 90 degree. So it will come in vertical direction and this bond will go on right hand side in both the cases. So our basic concepts will be applied, that with plus DIPT we will get below the plane attachment of oxygen, and with negative we will get above the plane attachment of oxygen, right? So what is the use of these groups attached here? In first case I have drawn the C6H11 group above the plane, and in second one I have drawn it below the plane. You can have two type of possibilities, that your oxygen should attach below the plane, right? But you may also have a product in which it is above the plane. It is very small in amount, but you can have this one, right? So when you have this type of structure, then this R is on the above the plane side, and you are doing epoxidation from below the plane side, right? So there is no hindrance due to this alkyl group to the epoxidation, right? So in this particular case you will get good amount of this epoxide, right? Suppose this is 98%, this is your 2% only. But in this case again you have here plus DIPT, not minus, this is again plus. So in this case when you are using this plus DIPT, it should again attach oxygen below the plane in the major product, right? You should have again, you will have these two type of products, right? Again, but this time this product is small in amount, right? You will get only 62% of this and 38% of this, means stereoselectivity is decreased, and the region of decrease in stereoselectivity is due to this alkyl group. This bulkier group is also below the plane, right? And because of its below the plane attachment side, epoxidation is hindered, because this epoxidation should also be below the plane because of our plus DIPT, but because of this alkyl group which is below the plane, your epoxidation stereoselectivity is decreased, right? That is why you are not getting a good selectivity in this particular case. So this example is very useful, and when you have more bulky group here, then your stereoselectivity will further decreased. So we will see a very important question based on it after this one, but remember this thing, right? So we have here again a peroxide titanium complex minus DIPT, right? So first we have to check that our OH hydroxymethyl group is on the right hand side or on the left hand side. So when you will rotate this double bond to in the vertical direction by 90 degree, it will go like this, and this bond is tilted downward, so it will go on the left hand side, right, and on which this OH is attached and rest part is attached, right. So because of this it is placed on the left hand side, your normal concepts that your this consideration will change, it will become opposite of it. So I would suggest only remember this one, that when you have on the right hand side you have to attach oxygen below the plane with plus det, right. Only remember this one and just do opposite with on the left hand side. Means when you have plus det or DIPT, you will get above the plane attachment of oxygen, and with minus det you will get below the plane attachment, right. So in this case you have minus det, your oxygen should go above the plane according to the previous concept, but because our hydroxymethyl group on the left hand side, so we will attach this oxygen below the plane, right. So you will get this type of arrangement. So we will see this example also. So it is based on the concept which we have discussed here, right. So I think this is very important. So in this case we are using all the condition required for sharpness epoxidation. We have plus det here, but in this particular case you have two allylic alcohol, this one and this one, right. So question comes that which allylic alcohol will participate in reaction. So for this first you have to understand that when you rotate this double bond, right, this bond is going upward, means it will come on the right hand side. So with plus det you should attach oxygen below the plane for first one, right. And for this one, when you rotate this one, your bond is going downward, so it will come on the left hand side, right. And with plus det you will get above the plane oxygen. So these two possibilities can be there, but only one allylic alcohol is participating in reaction. One is, suppose it is 1, it is 2, out of these two one is not participating. So in previous example we have seen that the attachment side of this alkyl group is very important, and I have told you that when this alkyl group will become more and more bulkier, stereoselectivity will decrease, right. So this oxygen from this carbon, this whole group is attached below the plane, right. And on this double bond, according to our concept, oxygen should go below the plane, right. So because the attachment site of oxygen and this alkyl group, this cyclic chain is same, so it can cause hindrance of attachment of this oxygen. So this allylic alcohol is called as unmatched, while for this one the attachment side of oxygen is above the plane, so this one is called matched, right. So only this one will participate, it will not participate. Only epoxidation of this allylic alcohol will take place, and on the above the plane side, right, on above the plane side. So this is very important. So I hope this video is helpful to you, and if you like my videos, please share my videos with your friends. Thank you so much for watching.